Hi again, Brian Miller-Hicks, continuing series of Earth Science and Geology PowerPoints. We're going to talk about mountain building. How do we build a mountain? You see all these beautiful peaks, ridges, summits all over the world. Do you ever wonder how they get there? Why they're there? Why they're where they are? Well, hopefully I can answer some of those questions. We're going to talk about mountain building. As you might guess, it has a lot to do with plate tectonics. Colliding continents make mountain ranges. Subducting plates make mountain ranges. Volcanoes are mountains. Mountains can be caused by faulting. So we'll look at those scenarios. Now the photo in front of you shows a mountain range up in Canada. And you'll note the layered rocks. As you know from your study of sedimentary rocks, layers are typically laid down flat at first, but they can be folded through tectonics. If they're buried deep enough, instead of breaking and fracturing through time, through a lot of time, through tectonic stresses, these layers of rock can fold. So we're going to be looking at folding as a cause of mountain building. We're going to look at faulting as a cause of mountain building. We're going to look at those scenarios. We've already looked at volcanism as a mechanism for building volcanic mountains. So let's look at folds. As I've already explained, rocks can be folded. Under enough pressure, buried deep enough, and with higher temperatures, rocks can act like what we call ductile materials. They have ductility, means they can bend and flow very slowly to some extent. With tremendous stress and pressure behind them, they can actually be folded. Here's a photo of some folded sedimentary strata on the coast of England, Dorset, England. The English coast is famous for some spectacular geology, and here we see some fairly thin layered sedimentary rocks that have been folded through tectonic stresses. Okay, so let's look at types of folds. This is a type of fold called an anticline. An anticline is a fold where you might think of an arch. Think of McDonald's Golden Arch, okay? The limbs or the legs of a fold on either side of the axis of folding. This is the axis of folding, sort of like a hinge, okay? The beds are flat, then when they get folded, a hinge is created, which forms an axis with a hinge line. And the beds on either side, left and the right, are limbs. And you notice in an anticline, an arch, the limbs are descending or pointing away from the fold. They're descending away from the hinge line. They're arched upwards. Okay. Now let's look at the stratigraphy here. As you know, the older the bed, the deeper the position of the bed is if there's no overturning. So this is the oldest bed, and this is the youngest bed. If we were to erode this anticline along its crest, we would see exposed in the center the youngest beds, and then the older beds successively, In this case, actually we're seeing the oldest bed exposed in the center, because this is the center bed, which is older than this bed and older than this bed. So the core of the exposed anticline will show the oldest beds and the younger ones further out. This is younger, this is younger. Okay, pardon my mistake, but I corrected myself. So we're all good. Okay, here is a broader scale picture of folding. You see an anticline arched up and another anticline here, and in between we have something called a syncline. A syncline is a warp or a fold where the beds are dipping into a basin, sort of. Anticlines form sort of like hills or mountains that arch upwards. Synclines in between form basin or low areas in between. Okay. You might think of here's a anticline arched up, and here's a syncline arched down. One way to remember, maybe if you want to use word techniques, is to think of syncline as a sinking basin-like structure where the folds are pointing downwards. In an anticline, the folds are pointing upwards. Again, if you look at the age of beds, if you look at this area, the oldest bed, the older bed, not the oldest, the older bed is exposed in the eroded center, and these beds are younger on either side. In a syncline, the opposite is true. The youngest beds are exposed in the center, with the older beds on either side. Let's look at fold geometry a little bit more in detail. It's described by the geometry of the hinge. Okay, not only can rocks, sedimentary strata be folded, but they can also be tilted. The tilt is called a plunging fold. A plunging fold has a hinge that is tilted. So in other words, this is the hinge, and now it's tilted away from us. Okay, this is a non-plunging fold. Again, this is an anticline with the oldest bed exposed in the eroded center. Okay. Now here's another photo of a famous anticline called Sheep Mountain in Wyoming. It's an anticlinal fold that is plunging due to erosion. Older strata, this is the oldest strata, are exposed in the center. Remember the arching upwards? This bed here is an old bed that's older than the beds on this side and the bed on this side. The monocline is also a fold type, but instead of forming an arch or forming a basin, it forms sort of a drape, and it's caused or created by faulting, where a fault causes this block of rock to move upwards, this block of rock to move downwards. This creates sort of a warp in the bedding, and the folds are draped over the fault because the fault has moved this block of rock upwards. Okay. Here's a dome. A dome is sort of an anticline, but it's an anticline where the upwarp is symmetrical all the way around. So a dome, you might think of it as a bubble. Everything's arched upwards uniformly all around. That means beds are dipping away from the center all around the dome. This is a symbol of strike and dip. Let's look at this part of the T, which signifies that the beds are dipping down away from the center, dipping down away, dipping down and away. Again, a dome being a type of anticline, the oldest strata in an eroded dome are exposed in the center, and the youngest strata are symmetrically arranged around it. Now, if this were a non-eroded dome, okay, if you didn't have this erosion, then you would see the youngest bed on top. But since it's eroded, the erosion has eaten through the beds and exposed the oldest bed in the center. Here's an actual dome in the Black Hills of South Dakota. Now this is a different type of dome. This is not a sedimentary dome. This is actually caused by an intrusion of igneous rock. The granitic rock in the center is pushed up as it intrudes, has folded and warped the beds around it, and formed a dome formed by intrusion. This is the opposite of a dome. This is a basin. So in this case, all the beds dip down towards the center, and since this is an eroded basin, the youngest strata are exposed to the center, with the older strata around the sides of the edges. This is the Michigan Basin. This is what's called a geologic map. A geologic map is a map that geologists use to look at the structure of geology, look at the beds, look at the type of rock and the age of rock in a particular area. And most geologic maps are actually kind of like works of art. They're very colorful, they're very well drawn, and they depict and show us a lot of information. So this being a basin, the youngest rocks are Upper Pennsylvanian, and that shows in the yellow. Remember, in a basin, this is a cross section of the basin. The youngest beds are the yellow Upper Pennsylvanian, and they're exposed in the center. The older beds are arranged in circular fashion around the youngest beds because of the down warping of the beds. The oldest beds show up around it as you go away from the center. Okay, let's look at mountain structure that's caused by faulting. A fault, as you know, is a break in rock. It's a fracture, but not just a fracture. It's a fracture along which movement has occurred. Okay, so in order for a fracture or a crack in rock or soil to be called a fault, there has to have been some movement along it. Now, as you might imagine, there are different kinds of faults. Let's look at some terminology related to faults. In this case, terminology that came about through mining. If you envision this red stripe here being a fault trace, on the right side of the stripe, this block is moved down. On the left side, this block is moved up. If you were to dig a tunnel along this fault, this miner is now standing on this floor, which comprises, on this side of the fault, comprises the foot wall. His foot is on it. He's hanging his lantern on the wall that's overhanging him, tilted and overhanging him. We call that a hanging wall. Okay. This is a normal fault in which the hanging wall moved downward, the foot wall moved upward, relatively speaking. Now, why would we mine a fault? Why would we look for a fault and put a mine through it? Well, it happens that mines, being fractures in rock, are very susceptible to fluids moving up and down and through them. The rock in the fault itself is usually crushed or powdered with lots of spaces and avenues for water to go up and through it. So when hot water goes through these fractures, as the water cools, it leaves behind various minerals, including precious metals like gold and silver. That's why we find mines following along faults. Let's look at structurally what faults look like. Let's look at the first one, which is normal faulting. Normal faulting means the hanging wall drops relative to the foot wall. This occurs in a tectonic scenario where we have pulling apart, a rift valley like the Rift Valley of Eastern Africa, or the rifting in Iceland, or the rifting and pulling apart on the sea floor along the mid-Atlantic ridge. This causes blocks in the center to drop down. It's characteristic of normal faulting. So normal faulting is caused by tension and pulling apart. And when this happens, you can have elevated ridges with basins in between. So you get kind of like a mountain range. If you look at a map of Nevada, a topographic map of Nevada, you'll see exactly that. You'll see a mountain range with a basin in between, another mountain range, another basin, another mountain range. This is known as basin and range topography, characteristic where the crust is being stretched apart by tectonic tension. Okay, let's look at the opposite of normal faulting, which is called reverse faulting, reverse and thrust faulting. A thrust fault is just a reverse fault with a low angle of dip. So reverse or thrust faulting occurs where we have compression, where blocks of rock are squeezing or grinding up against each other. What tectonic scenarios does that occur in? Well, when we have two colliding continental blocks, we can get that tremendous compression causing blocks to upthrust relative to each other. And that's where we see a lot of reverse faulting in and under compression. Finally, we have shear faulting, where we have very little relative vertical movement. Most of the movement is back and forth or sideways, where one block slides relative to another block. We call that strike-slip faulting or shear faulting. The San Andreas fault is an example of a strike-slip fault. Okay, so we have tension, pulling apart for normal faulting. We have compression, pushing together for reverse faulting. And we have side-to-side sliding for strike-slip faulting. Here's another look at normal faulting and how a normal fault block mountain range is formed. We have a fault just forming here. The hanging wall drops relative to the foot wall, and that forms elevated ground on this side and lower ground on this side. As time progresses, erosion continues, the lower side gets lower, the upper side gets higher as the fault continues to move, pushing this side up and pulling this side down. In the long term, you may get erosion of this mountain or range of hills to where the topography again is flat. Okay. Example of fault block mountains. Again, you have stretching, normal faulting with ridges and basins in between. Ridge here, basin here. Ridge here, basin here. Now, if you have a ridges pulling apart, forming basins, that's called Horst and Graben type topography. It's a German term. The Graben is a subsided or sunk block, and the Horst is the elevated block. A depiction of a normal fault on an outcrop, where you see, here's a geologist's sketch of what's going on. So this is a very clear, easily visible bed that should be horizontally continuous, but because it's been faulted, it now shows displacement. The total amount of displacement from the top of this bed to the top of this bed, part of the bed, is this amount of feet. So this block has dropped, and this block relatively has been lifted up. And this is the fault zone, the fracture along which movement occurs. Let's look at reverse faulting some more. Hanging wall moves up relative to the foot wall moving down relative to the hanging wall. This can also cause elevation of one block relative to another block. Again, here the tectonic forces are compression, building mountains because the hanging wall goes up and the foot wall goes down. Here's a reverse fault on an outcrop. This is what the geologist has drawn out. This bed, this is the marker bed, very clear, very visible, easy to see how faulting occurred. So this part of the bed used to line up with this part down here. And then because of faulting, it broke and was thrust up over this part of the bed. This part of the bed is the same rock is this part of the bed, but this piece broke and slid up and over this piece down below. That's reverse faulting or thrust faulting in this case. Here's another thrust fault. Now, if you weren't an expert geologist and you didn't know what you were looking for, you might miss this fault because these beds almost look like they're continuous across the fault, which is this line through here. But in fact, if you were to look at different, let's say, fossils and other types of structures from one bed relative to the other bed on either side of the fault, you might see a difference in texture, fossils, and so forth. So that would lead you to map this as a fault because there's this bed here is not actually continuous with this bed. It's been broken and this block has been thrust up and over. Here's a graphic showing that process, and also shows an interesting phenomenon that makes older beds get on top of younger beds. So let's look at this section. Precambrian rocks are very, very, very old, older than 540 million years old. Here's the thrust fault as it's forming. And the next picture shows this wedge of rocks starting to slip and slide up over this block of rock. Here's the thrust fault. The stress, again, is compressional, squeezing and pushing. This continues the process, and this is known as an overthrust fault because older rocks, the blue Precambrian rocks, now lie over younger Cretaceous rocks. Here we go. This is the present day situation where the old Precambrian rocks are on top of the younger Cretaceous rocks. If you look at this little mountain here, this is the erosional remnant of Precambrian rocks, very old rocks, sitting on top of younger rocks. This mountain is called Chief Mountain, and here's an actual photo of Chief Mountain, old Precambrian, sitting on top of Cretaceous. So roughly 500 million year old or older rocks sitting on top of perhaps 65, 80 million year old rocks. The third type of fault, again, is shear faulting or strike-slip faulting, where the sense of motion is shearing or mostly horizontal stress. It displaces along this fault zone. You'll note in this picture, this depicts a river. What's happening to the river here? Well, as the river flows, let's say it flows from right to left, it's flowing along. This used to be a continuous river before faulting started. Then faulting occurred. This block moved this way. This block moved this way relative to each other. Now, when the river hits the fault, it takes a right angle bend to flow along here, and then another right angle bend to continue its flow down slope. So when you see rivers with right angle bends, you can bet that those bends were caused by faulting. Sharp angled bends like that typically occur because blocks have been displaced. Here's a closer look at that. We have the active fault trace. This is the active fault. We have a linear valley, and we have what we call offset drainage. So this river was flowing from here down in this direction. It encountered the fault, and the fault actually moved this block, moved this block. Now the river has to take a right angle turn, a drastic right angle turn, and then another right angle turn. A sag pond is an area of ponded water because a fault zone often has crushed rock within it, which may weather to clay which may cause impedance or stopping of water flow. So water tends to pile up against clay material, which is not permeable and won't allow the water to flow through. Mountains often are marked by fractures and joints. They're not necessarily made by fractures and joints, but I want to indicate this to you because you'll see fractures and joints in mountains, and it's important to remember the distinction that a fracture or a joint is a crack along which no significant movement has occurred. Joints and fractures occur because of cooling in igneous rock or because of tectonic stresses. Here's a pretty famous mountain, Devil's Tower in Wyoming, where you have joints that are formed, joints or fractures that are formed by cooling of this igneous rock. Those of you who are old enough to remember a movie called Close Encounters of the Third Kind, this Devil's Tower is featured very prominently in the plot of that movie. So let's talk about mountains in the large scale. We can see individual mountains that are made by folding, by faulting, by breaking along faults, by folding from collision or from upwarping or from downsinking. All sorts of tectonic movements can make mountain ranges. So a lot in the earth today, we have lines of mountains that we can see along continental margins, and you might be wondering why that is. The growth of mountains and mountain ranges actually leads to the growth of continents. Let's look at this old picture of tectonics that you're familiar with. Plate subducting on top of the weak ductile asthenosphere. It collides in a sense with the continent. Now, what's happening here? As you know, a subducting ocean plate, subducting underneath another ocean plate, can form a chain of volcanic islands, volcanic island arc. As subduction continues and this plate is now subducting under a continent, that former island arc is forced, pushed, squeezed, plastered against the edge of the continent. Now it becomes part of the continent. That's why we see some continents with very, very ancient volcanic mountain ranges within the continent itself that were formerly formed over an ocean plate, plastered against the edge. This shows another depiction of that. Here's a subducting ocean slab, a volcanic island arc, and now subsequent in time, the volcanic island arc is plastered onto the edge of the continent, forming a continental volcanic arc. All this material in between, which was seafloor, is now being deformed and upthrust and squeezed up against the edge of the continent in what we call an accretionary wedge. So if you look at California, for example, the coast ranges of California are an accretionary wedge of former seafloor that, because of subduction, have been pasted up and forced up and squeezed onto the edge of California. If you look at the coast range and look at many, many outcrops, road cuts, etc., you can see rocks that were formerly ocean floor rocks now plastered up against the continent along the seashore. There's a continental collision zone, of course, caused by the collision of two continental plates in mountain building scenario, in mountain building mode, if you will. The rocks are deformed. You have metamorphism, as we explained when we talked about metamorphism. We have many thrust faults forming. We have the uplifting of thousands of feet of rock into a mountain range. This is a depiction of what are called accretionary terrains. So all these colored pieces here are from somewhere else, if you will. The red pieces are former island arcs, now plastered up against the continental edge. Submarine deposits, the yellow, used to be seafloor rocks. So are the blue strips, ancient ocean floor. And here are pieces of other continents. So what geologists have figured out over many years of mapping and thinking and looking at different types of rocks and recognizing them for what they are, they now recognize that the western margin, for example, of the continental US is formed of many pieces and slices that have been plastered onto it due to tectonic movement and have formed mountain ranges in the process. First major mountain belts, Andes Mountain and the western US are fairly young. The yellow area here forms the Alps, Himalayan mountains, which are very young, and other mountain ranges. Now let's look at the interior of these continental masses. The oldest parts of our continent are what we call shields and stable platforms. So the gray and the light red form sort of the cores of these continental land masses. And these very old, Precambrian in some instances, very, very old rocks of the cores of continents are surrounded by younger rocks, some of which have been plastered up against and around the older rocks, forming what we know now as the larger continental landmasses. Finally, we can have mountains of a sort formed not by tectonic collision, not by subduction, not by volcanism, not by faulting, and not by folding. We can have elevations or landforms or topographic relief formed purely by erosion. This is the beautiful Monument Valley region in Utah and Arizona area that's formed purely by erosion. These are formerly flat-lying sedimentary rocks which in times past extended and connected with each other and now are exposed as isolated mesas and buttes and spires purely by erosion through time.